Hey guys, welcome back to chemistry. Today we're going to talk about acids and bases, and specifically we're going to talk about titrations. And so I have my titration equipment right next to me. You will have already seen me titrate in class, but just to quickly refresh and show you what stuff we have going on here. So you have a base of known concentration in your burette. This is called the burette, and it has gradations on it. You can't really see it with the camera, but you can see exactly what volume you have in the burette. And then the bottom part here, this is called the stopcock, and you can turn it and liquid will come out, and then you could turn it back and liquid will stop, hence the name. And then I will have a flask, and you just put the flask underneath and raise the burette, and you will be titrating the base into an acid of unknown concentration. So whatever is in the flask is an unknown concentration. You could have it reverse where you have the acid going into a base, but the key thing is that whichever liquid you don't know the concentration of, that is in the flask, and the liquid you do know the concentration of is in the burette. The example we had in class, I titrated an unknown concentration of acid in the flask with a known concentration of base in the burette. Okay, so let's talk about how to use the titration equation and go from there. So we're going to use this equation, the titration equation, which is on your reference table T. And to understand the titration equation, you really need to understand molarity and what it means. So I'm going to take some time to talk about both of these equations. So the overall idea is that we're trying to find the equivalence point. We're trying to find the point at which you have an equal amount of acid and base. And if you're using a strong acid and a strong base, which is what we will use in Regents chemistry, then you will get an equivalence point of 7, about 7. So that is when you are neutral and you have the same amount of acid protons, or H plus ions, as you have of base ions, which are called hydroxide ions. So our goal is to get to this point, this neutral point where you have the same amount of acid and base. And that's why it's called equivalence point, because you have the equal equivalent amount of acid and base. So on the screen I have the two equations that I stole from your reference table T. I have the concentration equation and I have the titration equation. So like I said, to understand the titration equation, you really need to understand the concentration equation. And to break down quickly what the concentration equation means is basically the more moles you have in a certain volume, then the more concentrated you are. For example, if you have a glass of lemonade and you have more moles, or just like more sugar in the lemonade, then it will be more concentrated. And if you have less sugar in the same amount of volume of your water, then it will be less concentrated. So molarity is always representative of how much stuff you have in a certain volume. And the more concentrated you are, the greater the molarity you have. Okay, so we still have to figure out how this equation relates to that equation. So you'll see that concentration, this one, has M and V in it, and titration equation also has M and V. The fact that there's the A here and the B here, that's just telling you that this side is the concentration of the acid. And so this is the acid side, and the other side is the side for the base. That's all the little letters mean. Okay, so let's say we are trying to find moles of something. We're trying to find out how much stuff is in a certain volume. Well, we would need to get moles by itself, so to do that, I need volume to go on to the other side. So I'm going to multiply both sides by volume, because volume is being divided at the moment. And we will get a new equation, which is V times M equals moles. Notice how V times M is very similar to what's over here, where we have M times V equals something. So what this equation, how it's related, is saying the molarity times the volume is equal to the moles of your acid. So really MA times VA is the same thing as saying your moles of acid is equal to MB times VB. Remember, V times M equals moles. So your moles of acid equals moles of base when you are titrating and you're at your equivalence point, where you have the same amount of acid, your H plus protons, as your base, your OH minus ions. So this is just telling you when you've reached your equivalence point, you'll have the same amount of acid as you have base, so it's neutralized. Which again, going back to our lab, oh, I have it on this one. So like I said here, the equivalence point where you have equal amounts of acid and base, it was 7 here because it's a strong acid and a strong base, so they perfectly cancel each other at 7. And so that is what we use the titration equation for, is to figure out when you are at your equivalence point and how many moles of each you have. So let's try to use the equation. Alright, let's go for number 4. And I'm just going to move the screen. Okay, so here's a problem where it says, if it takes 54 milliliters of 0.1 molar NaOH to neutralize 125 milliliters of a hydrochloric acid solution, what is the concentration of the HCl? Okay, so we are going to use our equation for titration and neutralization, like the directions say. And so we need, I always like to write the equation first. So we have MAVA equals MBVB. Now the key thing is that your volume needs to be in the same units as what's on the acid side and on the base side. In this problem, they nicely give you both volumes in milliliters, so you don't have to do any converting. And so let's just plug it in. So we have 54 milliliters of and 0.1 molar NaOH. So that is our NaOH is our base. You need to identify which one is the base and which one is the acid first. I know HCl is our acid because, again, based on Arrhenius's definition, it has the H first, and the proton right there is what makes it an acid. And I know that this is our base, our sodium hydroxide, because it has the OH part second, and so that is what makes it the base, again according to Arrhenius's definition. Okay, so let's plug in. So it says we have 54 milliliters of our base, so I'm going to just write it in there. And we have 0.1 molar, this is capital M, so it means concentration, which is our M right there. Again for the base, so I'm just going to plug it in right there. Equals, and then they give us the volume of the acid, which is 125 milliliters. That's about M, sorry. And we don't know the concentration of the acid. Ma is our X. So to solve for X, you want to move this 125 milliliters to the other side. So I am going to, because it's being multiplied by x here, I'm going to divide it. Always do the opposite sign. So I divide it on both sides. So then you can just plug into your calculator 0.1 times, because it's m times v, so it's 0.1 times 54 divided by 125. And when you plug that into your calculator, you will get an x, your concentration of your acid, is equal to 0.04 molar, capital M. And that is for our acid, which is HCl. So, yeah, you just use the equation. Okay, let's try another one. So, for number 5, it says, if it takes 25 milliliters of 0.05 molar HCl to neutralize 345 milliliters of sodium hydroxide, what is the concentration of the sodium hydroxide solution? So I started this problem by just writing my equation again. We know that this is a titration because you're adding acid to the base, and we don't know the concentration of the base. So that's when we use titration equation. And because we know the concentration and volume of the acid and we don't know the concentration of the base, this equation makes sense to use. So let's plug in what we know. Well, first of all, we again have to identify who is the acid and who is the base. So because this is HCl, it's written where the H comes first. We know that that is the acid. It's called hydrochloric acid. And NaOH is a common base. It's called sodium hydroxide. It has the OH in it, which is what makes it a base. So this is our base. Okay, so I'm going to just plug in what it has. Again, I check that my volumes are in the same units. That's 345 milliliters and 25 milliliters. So we don't have to change anything. So let's go right into it. We have 0.05 molar HCl. And we have a volume of 25 milliliters equals, we don't know the concentration of the base, that's our X, because it says what is the concentration of the base. But we do know the volume of the base, which is 345. I didn't write units because they're the same units, milliliters and milliliters, so they will cancel when we divide them. So I'm not worried about them. Okay, so same as before, we are solving for X. Because 345 is being multiplied by X, we want to do the opposite sign and divide it to get X by itself. So we're going to divide both sides by 345. And so we have 0.05 times 25 divided by 345. And so we get an X equal to 0.0036, which I am going to, yeah, we can keep 2 sig figs. I know you all love sig figs. 0.0036, we know this is molarity because that is what we were solving for, molarity of the base. So it's molarity of sodium hydroxide. Remember, I do not want to see any numbers that don't have units. So pay attention to where your X is and who you're solving for. In the first problem, our X was the molarity of our acid, so that's how I knew to write the unit molar, capital M, for our acid, which is the HCl. And for this one, I knew we were solving for the molarity of the base, so again, it was molar for NaOH. Okay, so we are gonna stop there for now, and I just wanted to quickly remind you that the whole point of using this titration equation is that we're trying to get the same amount of moles of acid as we have moles of base, because that is when it is neutral, and for these strong acids and strong bases. So that's why we are using this equation.